In this video, we're going to talk about features of graphs for functions of two variables, or surfaces as we've come to see them. And specifically, things to look for or things to try when you're being asked to identify or to sketch those kinds of graphs. There's some key features here that we'll talk about, but we're going to talk about them in context of particular examples. There are also things that you would see if you're trying to identify or learn how to graph single variable functions. You'd look for where the heights are positive or negative, where they do take on different signs, where might that happen, and also some substitution games where we might plug in x equals 0 or y equals 0 into the function that reduces it to a single variable function that you might recognize, and then we can extend that outside of that constraint. We might also sub in other values of x and y to see what happens. And also moving away from x equals 0, y equals 0, we could look at what happens with large values of x and y. What does the function do when you get to the extreme ends of those variables? This kind of construction or this kind of experimentation is stuff that you would have seen before, plugging in values. What is new are some patterns that we're going to see in the formulas for functions of two variables. One is if we see a linear function, and we literally mean there the f is equal to some constant times x plus another constant times y plus maybe a third constant, then what we're going to get as an object there is a plane. That should seem fairly reasonable as an extension of the straight line formulas, m times x. What is new is if we see x squared plus y squared, if they always appear together, then what we get out of the graph is something that has circular symmetry. And what that means is if we sketch out our graph, if we go out to some point here and get a z value back, we are going to get the same z value back everywhere in a circle because x squared plus y squared is going to be the same at all points on a circle. Just because of the nature of the examples we'll see in this course, we're going to see that theme fairly frequently. So if you see something that has circular symmetry around the z-axis, then you'll be looking for a relationship in the function that has x squared plus y squared always appearing together. Last but not least, if we only have one of the variables actually listed in the formula, then what we have is a simple one variable function, but stretched out. So if we had a function like f of xy equals cos of x, let's do cos of y, then what we'd see is y is the only thing that matters, and x doesn't appear, doesn't mean that it doesn't show up in the graph, it just means that it has no effect on the heights. So if we change x, we don't change heights. And what we would see there is a cos graph, but we'd see it reflected as a pattern along the x-axis unchanged. So we'd see the cos graph like a ribbon stretched out. Doesn't matter what x is, we're still going to get this up and down motion as we increase y. So if you see a ribbon, one of the ways to achieve that is to have just one of the variables in the function. If we see something circular, you're looking for the x squared plus y squared as part of the formula construction. In this example here, we start off with literally f of xy equals x squared plus y squared. And so we see right away that this has circular symmetry. And if that's the case, we can see that here. If we pick a height and look around, we can see all the points in that circle have the same height. Same as we go to the corner here. If we wanted to redraw this, what we could do is do something like let x equal 0. If we do that with this function, we get z is equal to 0 squared plus y squared, or z equals y squared. Now if we were to sketch this ourselves along our x, y, and z axes, then what we just captured here was if x equals 0, we don't move out this way at all. We're actually staying in this zy plane. If we take that relationship, we get a parabola. So we get z equals y squared. If we combine that then with the circular symmetry, that tells us what happens when x and y are traded off against each other. Well, we've just figured out that that's going to give us a circular pattern. And so what we get here is a parabolic bowl shape. There's going to be this bowl at the bottom. It's going to be circular symmetry. It's going to have circular symmetry. If we look down from the top, it's going to look like circles. And this is just another way to represent that same surface, just cut off in sort of a square pattern. But it would look like this if we looked at a round region in the XY plane. Circular symmetry from the formula, and a way to get the basic shape underlying that by letting x equals 0 as a sample point. In this example here, we see a similar kind of scenario. We have the x squared plus y squared, which indicates, again, circular symmetry. And we can do the same game once we've done that, letting x equals 0. If we do that, our function is going to be e to the negative 0 squared plus y squared. And that is e to the negative y squared. Again, we sketch out our axes in x, y, and z. And the graph of e to the negative y squared is our classic bell curve. If we capture the relationship between y and z, we're going to get this bell curve that goes down like so, towards the negative axis in y here. Then we throw in the circular symmetry, and we get this sort of flattened hill shape with a peak at x0, y0. And that's in fact exactly what we have in the diagram here as well. So we can see the relationship between the formula and the shape of this graph. Now let's try one without the visual available to help us right away. We have the function. It has x squared plus y squared, so again, circular symmetry. We do like that because it simplifies things. Then if we imagine a cross-section through x equals 0, if we let x equals 0, we're going to get z equals the square root of y squared. And this is always the positive root. There's no negative there. So what we'd get there is z equals positive y for y greater than 0. Well, actually, this is the absolute value function, because if y is negative, we're going to get the absolute value of y for y less than 0. We take a negative value and square it, it goes positive. We take a positive root, we're going to get positive values back. And that translates very quickly into a nice sketch out of the graph. The relationship between y and z is a straight line, like so. And if we go in the negative direction, we have another straight line. Throw in the circular symmetry, and all of a sudden we have a cone. Tip vertex down here at the origin, because we capture the relationship between z and y when y is positive, and we have the x squared plus y squared indicating that things are always going to happen in circular patterns. That gives us only one possible shape for this surface. Another much more simple example here. We have no x squared plus y squared, so it's not with circular symmetry, not circularly symmetric. In fact, this one, though, has a different structure. It is linear in x and y. And that indicates that we're talking about a plane. Now, it's incredibly hard to sketch planes at different angles, different slopes. When we're talking in 3 dimensions and drawing it in 2, you really do need shading from a computer software to make the depth work out or be visible in a way that makes sense to a reader. But this definitely is going to be a plane, and it's going to have some kind of straight line underlying shape to it. Again, this is why we don't ask you to sketch these kinds of graphs typically, because it's very hard to do in a meaningful way doing it by hand. Here in our last example for now, we have a function of x and y, but the y does not appear. And again, what that means is if we change y, that doesn't matter for the height of the function. Z stays constant. And what that means is, say we're at a point here, if we go up to the graph and find the z value, as we change y, we stay at that same height all the way along. What does change the value of the function is if we go out in x here. So imagine, I'll put our axis actually where I think it should be, right around here, because sine of 0 is 0. And then as x increases, we trace out a sine graph that then gets duplicated or stretched out along the y-axis. So when we have a variable missing, what we see is a regular function just stretched out into the other dimension that's not mentioned in the formula. In your practice problems, you're going to see a number of these kinds of graphs and these kinds of formulas. If you're ever in doubt about trying to match them, all of the examples that we look at can be matched by looking at these kinds of features and the features about linearity, circular symmetry, or a missing variable. It takes a little bit of practice, it takes a little bit of insight, but these strategies will get you through all of those examples.